So this lesson's on sigma bonds, pi bonds, and hybridization. So when you have two hydrogen atoms, you have their electrons in their s orbitals, they each have one electron, and when those two orbitals overlap, they can share those electrons, giving them both full outer shells. Both orbitals are filled with now two electrons. The electrons are shared between the two atoms, and you have a covalent bond. This has got a special name. When you have this direct overlap of two orbitals, we call it a sigma bond. Sigma bonds can form via direct overlap of s orbitals, direct overlap of p orbitals, and a direct overlap of an s and a p orbital. That's as we can see here. But what about double and triple bonds? Well, electrons are negative, right? And electrons repel each other. So there's no space for more electrons to go directly in between the two atoms. So how do double and triple bonds form? Well, we talked about sigma bonds being this direct overlap, the electrons existing between the two atoms. And just a reminder that orbitals are regions of space where you're likely to find the electrons, and the sort of overlap area is a region of space where you're even more likely to find the electrons when they bond, because that's where the electrons are sort of comfortably held together by the positive attractions from the nucleus and sort of held in place. But still, it's just an area you're likely to find them. Anyway, so going on to the double bonds, there's no space there in the center. That's filled with the electrons from the sigma bond. So what happens is we get two p orbitals overlapping, but this time not directly overlapping head to head, but overlapping sideways. So you get this sideways overlap, and that's how we form a double bond. Now remember, you have different types of p orbitals. You have ones going up and down, left and right, and like this. So you can have an overlap up and down, and you can also have an overlap to the side. So you can get a double bond, which could be up and down, and then a triple bond could go on the sort of z-axis, or what's that, x-axis. Okay. So you've got the bond going head to head, single bond, sigma bond. Then you've got the bond, the overlap, what's the camera? The overlap like this, and then you can have an overlap like that for the triple bond. Okay, so double bond consists of one sigma bond. Sorry, single bond consists of one sigma bond. A double bond consists of a sigma and a pi, and a triple bond would consist of a sigma and two pi bonds. As we looked at before in a previous lesson, the pi bonds are not as strong as the sigma bonds. We'll look at some data for that later. Bond rotation. So normally sigma bonds, because you've just got the electrons held in between, the bonds can rotate. Okay, you have bond rotation, but when you have a double bond and a triple bond, those regions, that sideways overlap, causes there to be no rotation. Okay, let's do our first worked example. So have a read of this, pause the video and have a go. So can you calculate how many sigma bonds and pi bonds are in this molecule but2-ene-1,4-dioic acid? Okay, let's go through the answer now. So can you see you've got all of the non-double bonds, so 1, 2, 3, 4, 5, 6, 7, 8, they're just sigma bonds, that's 8 sigma bonds, and then the double bonds also contain one sigma bond, but also a pi bond. So you've got 3 double bonds, that's 8 plus 3 is 11 sigma bonds plus 3 pi bonds. So we can see we've got 11 sigma bonds and 3 pi bonds. Okay, the 3 pi bonds are in the double bonds. Okay, try this question now. So identify the number of sigma and pi bonds in the cyanide ion. So you're going to have to work out the Lewis structure first. So pause the video, have a go. Okay, and then the answer. So there's our Lewis structure for the cyanide ion. We can see we've got a triple bond. Triple bonds consist of 1 sigma bond and 2 pi bonds. Okay, here's another diagram showing a double bond in ethene. You can see here's the sigma bond, and then here's the overlap of the pi bonds. It's quite tricky to represent this in two-dimensional space, because what's going to really happen is those green pi bonds are actually going to properly overlap, but it's hard to represent that in 2D. On Cognity, there is a great three-dimensional model which you can sort of look at it from different angles to sort of understand how it sort of fits together. There's a link to that now. Yeah, we're talking about the bond strength. So a sigma bond of a carbon-carbon has this strength, 346. So you can see it takes a lot much energy to break it. a pi bond is not double. If it was double, it would be close to 700. But you can see adding that extra pi bond is not as strong as a sigma bond because it's not. You can see the way the electrons are held. They're not held directly between the two atoms. They're held sideways, so that makes the bond weaker. Same goes for the triple bond. This slide just looking at how we have, you know, how we looked previously at resonance. So in the ozone molecule, you have resonance. The actual model is in between these two states. It doesn't flick between these two states. It's in between these two states where the double bond is actually sort of partially here and partially there at the same time. Okay, moving on to hybridization. So now we're going to look at how hybridization forms. This is looking at orbitals again. So let's look at the electronic configuration of carbon. So have a look at this. I'll add some coffee. Yeah, so here we have the electron configuration of carbon. You can see the outer shell electrons, the valence electrons. You have 4 valence electrons. You have 2 in the s orbital and 2 in the 2p orbital. So thinking about how bonds form, so bonds form, or covalent bonds form, where each atom shares 1 electron, and those bonded electrons then will exist in that orbital. So you can see that the way this is shown for carbon, carbon really only has space for 2 bonds. It's got a space to share an electron here, so it can share an electron here and share an electron there. So it should only really be able to form 2 bonds. We obviously know it does, it forms 4 or 3. So how does that work? Because right now these electrons are in a filled orbital. There's no room for them to be shared. Well, what happens is something called hybridization. So carbon's lowest energy or ground state electron configuration changes during bonding in a process called excitation. So what happens is the ground state electrons get excited by absorbing energy in the bonding process. So this is carbon considered on its own. But once carbon has bonded, you can see that one of the electrons in the 2s orbital has been promoted to a slightly higher energy level, still same energy level, but it's a slightly higher subshell. And you can see how it's now got 1 electron in 2s, 1 in 2p, 3 in 2p, each in individual orbitals. This now means we've got 4 electrons available for bonding, which is why carbon can form 4 bonds. Now, that's what we already said. But this would sort of infer that, that carbon has different types of bonds. It suggests you've got 3 p orbital bonds and 1 s orbital bond. But that's actually not what happens. The bonds are all exactly equivalent. So a process must be occurring. And what happens is something called hybridization. And basically, it's where rather than having 3 electrons in p orbitals and 1 in the s orbital, this process happens where we get this equalization of those 4 different orbitals so that it will become equal and have equal energy, and this is called hybridization. There's 3 types we're going to look at, and the first is called sp3 hybridization. So here we've got the ground state. Here we've got electrons. When they're bonded, they get excited, they use some energy from the bonding process, one of them gets excited, but then what actually happens is they don't gain any energy to do this, to flick between these 2 states, but basically the p orbitals would lose a little bit of energy, the s orbital would gain that energy to get to a point where they are all exactly equal. So now we have 4 orbitals which are exactly equal, and we call them sp3 hybridized orbitals. So the reason we're calling them sp3 hybridized orbitals is because you've got 1 electron from the s subshell and 3 electrons in the p subshell. So we're using 1 s orbital and 3 p orbitals. We're making them equivalent, hence we call it sp3 hybridized orbitals. And this is showing how carbon normally acts and forms 4 bonds which are completely equal to each other. So these orbitals have different shapes to how they originally were, different orientations than their original orbital, and can form 4 strong bonds. we already mentioned this, that the total energy of the orbitals has not changed. It's just been like redistributed, so it's equal among 4. So let's have a look at that. So previously we had an s orbital and we had 3 p orbitals. We had one on the x-axis, one on the y-axis, one on the z-axis, z-axis. And now we can see when they get hybridized, they all become equal, and we get them all looking like this. So you can see there's 4 different, you can see an sp3 orbital looks like this. It's got this big area of space and this little area of space. Remember, this is the area you're likely to find the electrons. I think it's like 90% of the time. And they form around the central nucleus with a bond angle of 109.28, or you can remember 109.5 for easy sake, for simplicity's sake, around the central nucleus. So we've looked at this forming a tetrahedral structure. So we also get something called sp2 hybridization occurs. This occurs for carbon and other elements because sometimes you don't have 4 equal bonds. For example, carbon, when it forms a double bond, it forms it through a sigma bond and a pi bond. They're not equal. They have different overlaps, orbital overlaps. You've got the direct head-on and the sideways overlap. So it doesn't require the same level of hybridization as sp3. So sp2 is when you have like a double bond. Oops, why is it not going forward? Okay, so in sp2 hybridization, so again, this is for double bonds, we have this situation where we have not 4 equal orbitals. We have a situation where we have 3 equal orbitals ready for the 3 sigma bonds, but there's 1 electron in the orbital which is at a slightly different energy level. We can say that it's unhybridized. It's one of the p orbital electrons that does this, so that's why we call it sp2 hybridization, because you've got 1 s electron and 2 p electrons all hybridized, all being equal, all going to form sigma bonds, and then this extra electron which is unhybridized, which is going to form the sideways overlapping double bond or pi bond. So here we can see a diagram showing that we've got here sp2 hybridization. You can see the central carbon atom here has 3 sigma bonds, 3 directly overlapping bonds. Okay, the electrons are all in equivalent orbitals. Then we, also have 1 electron per carbon, which is in this unhybridized p orbital, which can then overlap to form a pi bond, and you see the pi bond forming there. So this occurs in alkenes in double bonds. Okay, and then finally we have sp hybridization. So sometimes carbon forms a triple bond, for example, E fine, C2H2. And it's going to undergo less hybridization because this time we only have 2, we can have two sets of 2 equivalent orbitals. So let's have a look. So in this situation, we're going to have 2 orbitals which we call sp, so that comes from 1 electron from the s subshell and 1 electron from the p subshell. Those 2 are equivalent. They're going to form our 2 sigma bonds, and then we're going to get 2 electrons which are going to be in unhybridized form to form the double and triple bond. So we can see that here. Here we've got the carbon, it's got a sigma bond here, a sigma bond here. That's from the sp hybridized orbitals. And then we've got the first double bond, which is a pi bond from the overlap of these 2 p orbitals, which are in the y-axis, and then the second pi bond from the overlap of the p orbitals in the y-axis. That would be the z-axis. So other atoms other than carbon also do this hybridization. It's very common. And to determine what type of hybridization the central atom or ion is going to have, we use electron domain geometry. So not electron molecular geometry, but electron domain geometry. So you're considering the lone pair as well. It's quite simple. You just got to remember that if there's 2 electron domains, so including lone pairs, you're going to have a linear, and that's going to form sp hybridization. So you're going to have 1 electron from the s, 1 electron from the p. You're going to have 2 hybridized orbitals. If there are 3 electron densities, so remember including lone pairs, we're going to get trigonal planar, sp2, so that's going to have 3 orbitals all hybridized, one from s, 2 from p, sp2, and 4 electron domains are going to have tetrahedral, sp3. So you need to remember linear, sp, trigonal planar, sp2, and tetrahedral, sp3. And you'll be required to go backwards and forwards. They might give you a trigonal planar structure and you need to remember that that's sp2, or they might give you sp3 hybridization. You need to remember that that's going to form a tetrahedral shape. So pause the video and have a go at these questions, and I'll go through them in a sec. Okay, let's go through the first one. So the first one was draw the Lewis structure, electron domain geometry, molecular geometry and hybridization for boron trifluoride. So Lewis formula for boron trifluoride, you see there's 3 electron domains. Okay, these are the steps that you have to follow. Once you've worked out the Lewis structure, you work out the electron domains, then you determine its shape. 3 electron domains, 3 bonding pairs, no lone pairs. Well, actually, it doesn't care about. You've got 3 electron domains, so it's trigonal planar. It did ask you for the molecular geometry, so therefore you do need to count how many bonding pairs and lone pairs there are. And again, this one's got no lone pairs, so its molecular geometry is trigonal planar 2. And then we identify the hybridization based on the electron domain geometry. So there's 3 electron domains. So if you remember from the table, that is sp2 hybridization. Next one is ammonia. Ammonia is our Lewis structure, 4 electron domains, tetrahedral, so therefore sp3. Okay, this one's CO2, so we got our Lewis structure. To add some more electrons, let's put some electrons here, 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 here. Sorry about the drawing. Anyway, looking at the carbon, we can see there's 2 electron domains around the carbon. Remember, double bonds count as 1 electron domain, same as triple bonds. So that gives us a linear geometry. Linear is sp hybridization. Okay, so have a look at this one. What would be the hybridization around each of the different carbons? So first you've got to work out electron domains and all that sort of stuff. So let's do it one by one. So first carbon 1, can you see there's 4 electron domains? That's tetrahedral. Oops, why is it not? So first one's carbon tetrahedral. So what's that going to be? Well, tetrahedral is sp3. Then we've got the second one, it's triangular planar, so that's going to be sp2. And the third one also triangular planar, so sp2 as well. So pause the video, have a go at these questions here. We can go through in a sec. Okay, so the first one, it's Lewis structure. There's methanoic acid. So we're considering well, there's 2 things to consider. We've got 2 different central atoms, but around the carbon, you can see, this is looking at oxygen first. Yeah, if around the oxygen, you can see there's 4 electron domains. Remember, we don't care about the molecular geometry for working out if it's sp or sp3 or whatever. We care about number of electron domains. So 4 electron domains gives us tetrahedral structure. So tetrahedral structure gives us sp3 hybridization, whereas the carbon, you can see there's 3 electron domains. 3 electron domains give us triangular planar, which gives us sp2 hybridization. Looking at methyl propanoate, we've got 3 sets of carbons which are equivalent. So carbon, all this carbon, this carbon, and this carbon all have 4 electron domains. This oxygen also has 4 electron domains. This one is missing on the diagram, but it should have electron domain, 4 electron domains as well. So you've got 4, 4, 4, and this one should have 3. Okay, so you can see if anything that 4 is tetrahedral, sp3 hybridization. Anything which is 3 is trigonal planar, sp2 hybridization. Right, last thing to talk about is hybridization in resonance hybrid models, things like benzene that we talked about earlier. So you can see in benzene we've got these carbons. They've all got 3 electron domains around them, but we've also got this delocalized electron. So we know that when you have 3 electron domains, you have sp2 hybridized orbitals, and that extra electron is then unhybridized and can form these sideways double bonds. But in benzene, remember, you have this sort of resonance structure where it doesn't flick between the two modes, but it can, you could get this almost like, it's not like a full double bond, it's resonating, and it creates this sort of structure that looks like this. So you've got the unhybridized, delocalized electron, which is able to move around the structure. So if you could pause the video and have a go at this question here, so we can determine the hybridization in ozone, and then have a think about its resonance. So drawing the Lewis structures, we can see it's two Lewis structures that looks like this, so it's going to be in between those. In each situation, we've got 3 electron domains around for the middle one, you've got 3 electron domains around the middle one here in each version of the Lewis diagram. So 3 electron domains gives you trigonal planar, so it's sp2 hybridized, but remember that that extra electron is able to resonate between these two states, well, it's in between these two states.